All right, hello. I'm moving on to the time series data analysis of this review project. So the time series, similar to a typical regression analysis, uses regression, but it is over time. So that is also what we're putting into factor, like we learned in the last in our previous videos. Once again, all right, let's actually start with the data set here. So obviously we have these data values variables moving over time. We have three variables that we're gonna observe: technology, capital labor ratio, CLR, and then output. So we can already kind of see that the output, or speculate that the output will be the dependent, and then technology or the capital labor ratio will be the X. Actually, capital to labor ratio can also be the Y, but we want the output usually to be the Y, technology to be the X usually. All right. So once again, we check if the data has any missing values. We didn't, but in the real world, it is most likely that you will. We shorten these variable names to make our coding more efficient, and then we use box plots and histograms to kind of observe what's going on before we deeply analyze them. All right, so output, nothing too irregular. We don't really have any outliers. We have a slightly right-skewed function or histogram, but output in general doesn't, like this output value of what it looks like to be between 0.6 and 1.3 doesn't really tell us much. But no outliers or nothing of that sort. No very skewed left or right distribution. Capital labor ratio looks actually more symmetric to a normal distribution. And even the box plot the median looks very close to, like, the very close to the max and the min, or between those. If the median was closer to the min, then we would have higher. Our high values will be relatively even, like, more extreme and higher, which would also skew our data or our histogram. Our tech actually is clearly right skewed, so maybe we can suspect that for a long time we didn't have a lot of good technology, and then recently we've kind of developed it more consistently. Same with the box plot. The median is clearly closer to the min, and then the max is kind of more far away. Correlation of these three variables. The technology and output variable have a very high correlation, and then we have the capital labor ratio and output having 36% correlation. So because output and technology are so similar, or are so highly correlated, we never want to put output and technology both as the explanatory variables, because then there's a high chance that these two variables will fight in multicollinearity, and we don't want that to happen. All right. Before we analyze the time series data set, we want to check if the time series model is actually a time series data set, because if it's not, then what it'll do is it'll use these date times as like a variable instead of like an actual aspect of time. And obviously we don't want that, because we're analyzing the other variables and associate to time. So any data set you're analyzing, you gotta analyze, check if data set is a time series first, which it is in this case. And then what we'll do is we'll graph get a good overview of how the data values are moving by each variable. We kind of see an upward trend for output. Capital labor ratio increases, and then it will later on decrease. And then similarly to output, we got PEC and output as having high collinearity. So not a surprise that PEC is also increasing over time. And our first assumption or requirement when we're analyzing these time series data sets is that they must be stationary, right? So these trends don't look very stationary because our requirement of stationarity is for these values to be similar around the mean, which it looks like they aren't. Now these values, y values, are also important to look at because obviously the bigger the y values, the more non-stationary it will get. But we want similar mean and variance, which the variance looks similar, looks pretty constant, but again, the visual test isn't the most reliable. All right. And so what we'll do is we'll use a formal test called the ADF test, the augmented Dickey-Fuller test. And we'll inspect the p-values. The p-values, none of them are passing, which means none of these are stationary. And recall that the way to make these data values stationary is to differentiate them or log them. I've actually tried logging some of these values, but they had some, no technical errors, but they didn't really display the results I wanted. But anyhow, differentiation is another appropriate method. So I did differentiate all of these three variables. So what we see is the mean looks actually like they're pretty constant, but the variance looks like it's moving around a lot more heavily. But recall what I said about the y values is these y values from 1 to 1.8 are actually a lot bigger than these y values over here. Or I guess looking at output alone, the y value range is a lot smaller. Let's look at for capital labor ratio. So this is from like negative 0.2 to 2, and then this one's from 2 to 3. So definitely a lot smaller. And so what we did by differentiating is we made it more stationary. Now we don't know if these values are stationary. There's no like direct threshold to how we can determine that, but we made the data sets more stationary, and by doing so, we get a more accurate and specific result of how these data values move over time. All right. So what you also saw in the GG display plots is the ACF and the PACF. Recall that the PACF differs from the ACF because the PACF removes some of these like past previous times of errors that may move on to the further lags. But nevertheless, it looks like the PACF and ACF looks pretty similar on all of these. And then note that the ADF test also like suggests a lag order for us to use. But formally, we use the auto.arima function to look at the ideal order of lags for each of these variables. And surprisingly, so we want to look at the first index. These other values of indexes are for something else that we might use in the future, but the first index we all get for each variable is 0. So 0, 0, and 0, which means um, just for output, we don't want like a previous value of output to explain our y variable, which is our current value of output. Same for technology. We don't want like a 1 unit in the past of technology explaining the current value of technology. Um, but what I've done here is I've lagged a past value of output anyway, just to look for the BG test. Recall that the BG test is looking for serial correlation, so collinearity between these like past and current values. So this lag of 1, every value is tested onto correlation onto the next plus 1 unit of time value. And the result of that is a high p-value, which means that we do not reject the null, and we confirm that our analysis has no autocorrelation. Because when we reject it, we conclude that we suspect that there is autocorrelation, but there is no autocorrelation. Just like how these PACF and ACF graphs are kind of telling us. The ACF and PACF for capital labor ratio, it actually passes the threshold, but by very small amounts. So usually we want to use a formal test for that, and our formal test says none of these past values of onto its autoregressive function are necessary. All right, so now for the distributed lag model, which utilizes time, but it's for the other explanatory variables, not onto itself. So when we regress output, we don't regress onto the past values of output, we'll do it onto tech. And for, like our intuition said, we'll make our output the dependent variable, and then we'll also regress it onto these other two variables that we have. Similarly to the previous regression analysis that we have done in our multiple regression, we utilize this BIC function of the lagged variables. Now, I'm pretty sure we can just say LM, but when we want to include time, we say DYNLM. Don't exactly know what that stands for. I could actually quickly check it, but all right, dynamic linear models and time series. So yeah, that is this DYNLM function is for time series. Right now, it's not very necessary, but this is quickly to check which variables are ideal for output, and clearly we get both capital to labor ratio and tech as a determinant for output. And so for tech and the CLR, we regress each of these variables, the output by these like different values of time. And what we'll notice is that our BIC value actually increases as we move further down the lag. And our ideal BIC model is just the tech variable without any time. Same with the capital labor ratio. Lowest BIC value is the one without any lags. So in an anticlimactic way, we actually conclude that the most ideal model is just actually the model without any time series lags. Now, we don't know if this value alone, or this value alone here, since this has the lowest BIC by far, we don't know if this is the actual ideal model, because again, we need to, if we want to do that, we need to test for like all of those like functional forms and reset tests and all that good stuff. But we do know, we have learned from these types of testing that the lagged versions of these independent variables are not actually necessary. And so we conclude that, that's what we conclude, is that the lagged versions of our AR or DL or AR DL, none of that is necessary, and that time doesn't necessarily play a factor into determining the relationship between output and then tech and the capital labor ratio. And So what I want to conclude from this as well is kind of the acknowledgments of our flaws of what I just did, because intuitively we want to. Usually there is like a trend between our technology and our output. So what I think may have gone missing is we kind of restricted our trend of our data too much, because up in here we clearly saw that there's like an increase within these like trends, right? But when we differentiated, there is no clear trend upon these data sets. So what I suspect is what happened between what happened to conclude of us getting no lag variables is we kind of we differentiated the data, which means we completely restricted their trends. Now, stationarity is an assumption, but we never want to restrict our trends too much to the point where we can't like forecast or analyze any trends within the data set. So that's what I suspect for what we happened here that led us to result of get the result of no lag values. But that's what we'll conclude based on our statistical test, is that we have no ideal lag values and we should just use a regular regression for this.